Hello everyone. In this lecture of the probability theory course, we will be talking about joint distributions. We will first cover the topic of joint distributions for discrete random variables, and then we will repeat our discussion but regarding continuous random variables, and finally we will calculate the expectations and correlation for joint discrete and continuous random variables. Let's start with joint distributions of discrete random variables. When we have joint random variables, that means that we have more than one random variables. Typically in this lecture we will be focusing on the case of two random variables, but in general when we have more than one random variable, we might be interested in finding the joint distribution. The joint distribution is the probability that the first random variable takes a certain value as well as simultaneously the other random variable takes another value. So we can see here that the definition of the joint probability mass function for the case of two jointly distributed discrete random variables is defined as the probability that the first random variable x takes a value small x and simultaneously at the same time jointly the second random variable y takes a specific value y small. So this is the intersection of the two events. Remember when we talked about the conditional probability and we said that the probability of one random variable given the knowledge of the other variable is calculated as the joint probability or the probability of the intersection divided by the marginal probability. This is what we mean by the joint distribution or the joint probability. It is the probability of the intersection, the probability that both events occur, and these two events are that the first random variable takes a specific value small x and the second random variable takes a specific value small y. And as we said before about the probability mass function of any random variable, there was some conditions that need to be satisfied such that this BMF is valid. So similarly here for the joint probability mass function, we have some conditions that need to be satisfied, and they are all meaningful conditions and they arise from our understanding for the probability distributions. The first condition is that the joint distribution, the joint probability mass function, is always positive or zero. So we cannot have a negative probability mass function or negative joint probability mass function because it means the probability, and this probability can never be negative. Similarly, the probability mass function for two jointly distributed random variables cannot exceed 1 because it means probability that the two random variables take specific values, and this probability can never exceed 1. Moreover, the summation of the probability mass function over all the possible values of x and y should be equal to 1. This is the rule of total probability. If we accumulate the probability that random variable x takes a specific value as well as y takes a specific value, this accumulation should add up to 1 if we consider all the possible values of x and y simultaneously. Again, this is the same as we described before about single random variable and the condition of its BMF, that the summation of the BMF over all the values of the random variable should be equal to 1. Finally, the condition which comes from the definition, it's not a condition, it's more like a definition of the joint probability mass function, that it is the probability that the first random variable takes a specific value and simultaneously the second random variable takes a specific value. Recall that at some point we were interested in the probability that a random variable, a single random variable, takes a value in a certain range. For example, the probability that the random variable x is between 3 and 7. And we used to calculate this probability by summation of all the probabilities that the random variable takes a value for all the values in this range. Similarly here, we can define any region A, but what we need to take care of here is that when we define region A for joint distributions, we mean a region or a range of X and a range of Y, a range of the first random variable as well as the second random variable. Then we proceed similarly as before, that the probability that the two random variable X and Y takes a value in the range defined by A is the summation of the BMF for all the values in region A. And again, since region A is defined by X boundaries and Y boundaries, that's why we have two summations here, summation over the values of X and the summation over the values of Y. Let's take a quick example to understand what might be meant by the joint PMF or the joint distribution. Let's assume that we have a box of 3 red balls and 2 green balls. And let's assume that we draw or select 2 balls at random from this box. We may define X as the number of red balls, in the sample that is selected, in the sample of the 2 balls, and Y equals the number of green balls. Of course, for each one of them, for each random variable X or Y on their own, we can find their BMF as we used to calculate before. But we might be interested in calculating the probability of X and Y, or the joint probability of X and Y. As we used before, let's start with determining the range of X and the range of Y. So what is the range of X? What are the possible values of the number of red balls in a sample of 2 withdrawn from this box? Of course, as you might think, we might have no red balls or 1 red balls, or both of them are red balls. So X can take values 0 or 1 or 2. Similarly, Y is the number of green balls, so by coincidence here, we might also have 0 or 1 or 2. So if we want to calculate the joint probability, remember for the marginal probability, we used to have a table like this, in which we write the values of X, and then we write the BMF of X. However, in this case, we have joint distribution, so we have 2-dimensional distribution. So we might find it using a similar table where these rows represent the values of X, which are 0, 1, and 2, and the columns represent the values of X, and the rows represent the values of Y, which might be 0, 1, and 2. And then for each cell, we write the probability that the number of that X takes a specific value and Y takes a specific value. For example, here we should write the value of the probability that X equals 0 and Y equals 0. Here we should write the probability that X equals 2 and Y equals 0, and so on. And we need to calculate those probabilities. Of course, some of these probabilities in this specific example can be calculated right away. For example, what is the probability that the number of red balls is equal to 0 and the number of green balls is equal to 0? This probability definitely is equal to 0, because we will withdraw 2 balls, or a sample of 2 balls. So in total, we will have 2 balls. So there is no way that we have 0 red balls and 0 green balls at the same time. So this probability in this cell is equal to 0. Similarly, what is the probability that we have 1 red ball and 0 green balls? Again, since the total does not sum up to 2 balls, which is the number of samples the number of balls we draw in this sample, then this event can never happen. We can never have one red ball and 0 green balls. So again, this probability is 0. Similarly, this probability is 0. Okay, let's for example find this probability in this lower cell. What is the probability that we have 2 red balls and 2 green balls? That is a total of 4 balls that we don't have. So again, this probability is 0. What is the probability of having, for example, here in this cell, what is the probability of having 2 red balls and 1 green ball? Again, this is 0. Similarly, you can say that this probability is 0. So we are left with these 3 cells which are meaningful or non-zero probabilities, or have non-zero probabilities, because in this cell we want to calculate the probability of having 2 red balls and 0 green balls. We can have this. Here, this cell represents the probability of having 1 red ball and 1 green ball. Again, we can have this, and finally this other cell. And if we want to calculate them, what is the probability of having 2 red balls and 0 green balls? So as we used to calculate before, it is choosing out of the 3 red balls 2 red balls, and choosing out of the 2 green balls 0 balls. This is the number of ways of selecting 2 red balls and 0 green ball, divided by the total number of ways we can select 2 out of 5, which is 5C2. Similarly, this probability here will be choosing 1 out of the 3 red balls and choosing 1 out of the 2 green balls, divided by the number of ways we choose 2 out of 5. And finally, this one will be from the 3 red balls we choose 0, and from the 2 green balls we choose 2, divided by the total number of ways, which is 5C2. Of course, as a double check, you need to calculate these values using the values of the combinations, and if you sum all these probabilities, that should total up to 1. So since most of the probabilities here are zeros, then as a double check you need to add that this probability plus the second plus the third one total up to 1, and of course they will total up to 1. So again, this example shows us what might be meant by joint random variables or joint distributions of more than one random variable. We have 2 random variables that might be related or might not be related, and we want to find the joint distribution, the probability that the random variable, the first random variable, takes a specific value and the second random variable takes another specific value. Another definition that might arise when we consider jointly distributed random variable is what we call the marginal probability mass function, or the marginal distribution. The marginal distribution is the probability mass function or the distribution of one of the random variables alone. So if we want to calculate the probability mass function of random variable x alone, we need to consider the probability that random variable x takes any specific value small x. So in calculating this, do we care about the value of y, the second random variable? We don't. So we want to calculate the probability that random variable x takes a specific value small x irrespective of the value of y, which means taking into consideration all the possible values of y. That's why when we calculate such a marginal probability, we have to sum the values of the joint distribution or the joint probability mass function over all the values of y, because for us the probability that random variable x takes a specific value is what we want to calculate for irrespective the value of y, which means, for example, if we want to calculate the probability that x takes a value equal 1, and let's think of it in terms of the previous example. So it is the probability that x equal 1 while y equals 0, or the probability that x equal 1 while y equal 1, or the probability that x equal 1 while y equal 2. So we consider all the possible values of y as long as we are calculating the joint probability for the specific value of x and any other possible value of y. This is what we call the marginal distribution or the marginal probability mass function. So again, when we want to calculate the marginal distribution of x, we sum the values of the joint BMF over all the possible values of y, and similarly, if you want to calculate the marginal distribution of y, we calculated by summing the joint distribution or the values of the joint distribution over all the values of x. Again, let's try to understand this through an example. This is the table of the joint probability mass function in the previous example, where we had box of 5 balls, 3 green and 3 red, 2 green, and we withdraw a sample of 2 and we find the probability mass function. So for example, if we want to find the probability that x equals 2, so what is the probability of choosing or having 2 red balls in the sample? Of course, we can calculate it on its own because we know the description of the problem, but here we want to practice calculating it from the joint distribution. So again, as we said, this is summation of the joint BMF at x equal 2 and y equal small y, value small y, for all values of y, which are from 0 to 2. So simply it is the probability that x equal 2 and y equal 0 plus probability that x equal 2 and y equal 1 plus probability that x equal 2 and y equal 2. Of course, we know from the problem that these two probabilities are equal to 0, but again, this is a coincidence in this problem. So where are these values? These are the values shown here in this column. So simply, if we add these values, we get 3 over 10. And similarly, if we add these values, we get 6 over 10. And similarly, this is 1 over 10. And these values in this last column represent the marginal distribution of x. Again, this value is the probability that x equals 0. This is the probability that x equal 1, and this is the probability that x equal 2. Similarly, we can calculate for the green balls or for the random variable y by calculating the marginal probability as follows. If we sum these, so these are the probabilities that y equals 0 and x equals 0 or 1 or 2. So this is the sum. We have 3 over 10, 6 over 10, and 1 over 10. And again, this column represents the marginal distribution of y. Of course, if you want to double check, the summation of these values is equal to 1. The summation of these values is equal to 1 because both of them is a valid probability mass function, and similarly, this one is the summation of all the probabilities in this box, which are the joint probabilities or the values of the joint probability mass function, which again, as we said, should sum up to 1. Since we have more than one random variable, we might be interested in knowing whether these random variables are dependent or independent. When we can decide or know that a random variable is independent of the other, as we said before when we discussed the conditional probability, if the knowledge of the value of one of the random variables does not affect or does not change any of the probabilities associated with the other random variables, then in this case the two random variables are said to be independent. So again, if the knowledge of the values of y does not change any of the probabilities associated by the value of x, then x and y are said to be independent. And of course, in order to say that two random variables are independent, we need to make sure that this condition is satisfied for any value, any specific value of the two random variables x and y. So that's why we have here that two discrete random variables are said to be independent if the events x equal a and x equal small x and y equal small y are independent for all the values of x in the range of x and all the values of y in the range of y. And in this case, we have this condition satisfied, that the joint distribution is equal to the multiplication of the marginal distribution. And again, this is what we concluded before, because for example, if we want to calculate the probability of x taking a specific value small x, given that y equal specific value small y, so this is the probability of the intersection of the two events. So this is the probability that x equals small x and y equals small y divided by the probability of the condition. So this is the probability that y equals small y. Again, if they are independent, that means that knowing y does not affect or change the probability of x. So in case they are independent, that should be equal to the probability that x equals small x. So simply, the joint BMF equals the multiplication of the marginal BMFs if they are independent. So this condition, we say that this condition is necessary and sufficient. Necessary means that if the two random variables are independent, then we can know for sure that this condition is satisfied. So if we know that the two random variables are independent, then their joint distribution equals to the product of their marginal distributions. And the other way around, if we know that this condition is satisfied, but we have to make sure that it is satisfied for all the values of x and y, then we can conclude that the two random variables are independent. So this is the condition of independence. And as we just mentioned, we might be interested in defining conditional probability mass function. So if we define f of y given x, so this is the probability that y takes a specific value of y given that x takes a specific value of x. So again, this is the joint BMF divided by the marginal BMF, as we mentioned a while earlier, and as we mentioned already when we discussed the conditional probability. Since this is a probability mass function, what conditions should it satisfy? Of course, it should satisfy the three main conditions of any probability mass function, that f of y given x for a specific value of y and a specific value of x, this should be larger than or equal 0. The summation of this distribution over all the values of y. Again, of course, recall that this conditional probability mass function is conditioned on a specific value of x. So it is not function of x, given that already we substitute with the given specific value of that random variable x, but it is function of y, or it varies with the values, the specific values of y. So if we sum over all the possible values of y, that should be equal to 1. And of course, you can easily verify this, because if you sum the joint distribution divided by the marginal distribution of x for all the values of y, of course, this one is not function of y, so it goes out of the summation. And the numerator, if you get summation of the joint distribution over all the values of y, that is equal to the marginal distribution of x. In this case, we have marginal distribution of x divided by the marginal distribution of x, which is equal to 1. And finally, the third line that we usually write is about the definition, that the joint BMF, the conditional BMF, is equal to the probability that y takes a specific value y given that x, or given the knowledge that x takes a specific value small x. Let's try this example together. It's a little bit more complex example compared to the examples that we solved earlier. However, it can be solved using the same idea. Now, in this example, we have two balls selected at random from a box which contains 3 blue balls, 2 red balls, and 3 green balls. So we have a larger ball in this case, and we select 2 balls at random. And we are given that x is a number of blue balls, so x equals the number of blue balls. So we can know that x can have a range of 0, 1 ball, or 2 balls, while y is the number of red balls, so y equals the number of red balls, and again this y is equal to either 0 or 1 or 2. Now, the difference here in this example compared to the previous example is that x plus y is not necessarily equal to 2, because the sample withdrawn might be a sample of 2 green balls. So in this case, the number of blue balls is 0 and the number of red balls is 0. So our table of the joint distribution will be more rich. Most of the cells will have non-zero probabilities. So he asks us to find the joint BMF of x and y. The probability that the sum of the red balls and the blue balls is most equal to 1, the marginal BMFs of x and y, and to know if they are independent or not, and finally the expected number of blue balls in the sample. So let's try this example together. So again, we have the box of 3 blue balls, 2 red balls, and 3 green balls. So as we used, let's write our table where x can be equal to 0, 1, or 2, and y can be equal to 0, 1, or 2. And each cell represents the joint distribution. So in order to have 0 blue balls and 0 red balls, that means that out of the 3 blue balls we select 0, out of the 2 red balls we select 0, and by default that means that out of the 3 green balls we select 2. So this is the number of ways we select 2 balls in which none of them is blue and none of them is red, and we need to divide it by the number of ways of selecting 2 balls out of the whole box, which is 8, so that is 8C2. Similarly, let's calculate one more together. What is the probability of this cell? This cell is the probability of selecting 2 blue balls and 1 red ball. Of course, we can't have overall 3 balls in a sample of 2 balls, so this probability is equal to 0. Similarly, this probability is equal to 0, and this probability is equal to 0. However, we might select 1 blue ball and 1 red ball, so that is 3 from which we choose 1, and 2 from which we choose 1, and for the green balls we choose 0, and again this should be divided by 8C2. Similarly, you can get the probabilities in these cells. For the second term, the second requirement, we want to calculate the probability that the sum of the number of red balls and blue balls is at most equal to 1. So first, let's define what is the sum of number of red balls and blue balls. That is x plus y. And we want to find the probability that this number is at most equal to 1. So that is less than or equal to 1. So if we want to calculate this probability, that means that we defined a region A, and this region is defined that by the fact that x plus y is less than or equal 1. So simply we can sum the joint distribution, the joint values over the values of x and y which fall in this region. Of course, the values of x and y which fall in this region are the values that x equal to 0 and y equal to 0, in which the summation is equal 0, or probability that x equal 1 but y equal 0, or the probability that x equals 0 and y equal 1. Of course, any other values will be falling outside the region of x plus y less than or equal to 1. Then from the table we can have these values as we calculated before and write their summation. If we want to calculate the marginal BMFs of x and y, that means we need to calculate f of x for the values of x, and again this is the summation over all values of y for the joint distribution, and again this can be obtained from the table. Of course, note that this is a BMF, so you should find the value of this BMF for every specific value of x. That's why we can use the table that we generated before. So we already know all these values. Once we perform the summation of the columns, so this is fx of 0, this is fx at specific value of 1, this is fx at specific value of 2, which means that these values are the marginal distribution of x, and similarly the values calculated by summation of these rows here will be the marginal probabilities of f of y. As a double check, we need to make sure that this summation is equal to 1 and this summation is equal to 1 as well. In order to check whether x and y are independent or not, we want to check if f of x and y, the joint distributions, equal the marginal distribution of x multiplied by the marginal distribution of y for every x and y, for every specific value of x and y or not. If this condition is satisfied, then they are independent. If this condition is not satisfied, even if for a single value of x and y, then the two random variables are not independent. That's why if we want to make such check quickly, you can check if the multiplication of this value here, for example, this value here multiplied by this value here, so this is the probability that y equals 0 times the probability that x equals 0, and to check if it is equal to this joint distribution or not. If it is equal, then you have to try the next value until you check all the 9 values in this example. However, once you find one pair of values that not satisfy the condition, then you can tell that the values, the random variables x and y, are not independent. Of course, in this example, they will not be independent, they will be dependent, because recall these cells here had probabilities equal to 0. However, this value is not equal to 0, and this value is not equal, and this value is not equal to 0. So the product of the value here and the value here will be a numerical value which is not equal to 0. That means that for these specific values of x and y, the joint distribution is not equal to the the product of the marginal distribution, and consequently the two random variables are not independent, so they are dependent. Finally, in order to find the expected number of blue balls, that is the expected number of the expected value of the random variable x. So simply we can calculate it as we used it before. It is summation of x f of x, which means that we need to know the f of x, which is the marginal distribution that we calculated in the previous step. This is another example in which we are given the joint distribution without knowing the meaning of the random variables or without having a description of the random variables. However, such problems can be solved exactly the same way as we used it before. So we have two discrete random variables, x and y, and they are jointly distributed according to the given equation, where x and y equals 0, 1, 2, and so on. So that is all the positive integer values from 0 to infinity. And the first requirement is to find the constant x, and then to find the marginal distribution f of y given x, and then from which we want to determine if x and y are independent or not. So for the first requirement, we want to calculate the value of the constant k. The way we think of calculating the value of the constant k is the same as we used before for single random variables. We want to make sure that the joint BMF follows the total probability rule, which means that summation of all the values of the joint BMF is equal to 1. So we want to make sure that the summation of f of x and y is equal to 1. However, since we have two distributions here, then this summation is really a double summation. One summation over all the values of x and one summation over all the values of y. So we have k, this is constant that can be taken out of the summation, for summation of x from 0 to infinity and y from 0 to infinity as well, for 1 over 3 power x plus y. This can be written as follows: 1/3 power x times 1/3 power y. This should be equal to k, and then since x and y are separable here, so we can separate the summations. So this is summation of y from 0 to infinity for 1 over 3 power y times the summation of x from 0 to infinity for 1/3 power x. Of course, each of these two summations is a geometric summation, a simple geometric summation. So that is k, and this is 1 over 1 minus third, which is 2 over 3, and the other one is similarly the same. And since this should be equal to 1, that means that k is equal to 4 over 9. So again, the main idea here, or the main way of thinking, is to make sure that the BMF is valid. What is the value of the constant that guarantees that the BMF is valid, which means that the summation of this joint distribution over all the values of x and all the values of y is equal to 1. For the second requirement, we want to find f of y given x. So this is the conditional probability distribution. So f of y for y given x, as we said by definition, it's the joint distribution f of x and y divided by the marginal distribution f of x. So in order to find this, we need first to find the marginal distribution. Again, the marginal distribution f of x is summation over y for f of x and y. And if we calculate this summation, we have the constant k, which we calculated as 4 over 9, times 1/3 power x. This is constant with respect to y, so it is taken outside of the summation over y. and then the summation of 1/3 power y can be calculated as a geometric series, which gives us 3/2. So by simplification, that will be 2/3 for 1/3 power x for all the values of x. So we have to specify the range of x by writing that x is equal to 0, 1, and so on. So simply making such a division, it's again k 4/9 for 1/3 power x plus y divided by f of x that we just calculated. That's 2/3 1/3 power x, which leaves us with 2/3 for 1/3 power y. So this is the conditional probability of y. That's why it is function only of y, given knowledge about x. Again, we have to specify the values of y, 0, 1, 2, and so on. And to answer the question of whether x and y are dependent or independent, we need to find the marginal distribution of y as well, and check if it is equal to the conditional distribution of y given x or not. You can either calculate it straightforward, and this is what you have to do every time, but from the symmetry of the problem that we can notice, we can say that f of y will be calculated the same way we calculated f of x, and eventually we will get an expression similar to this, which is 2/3 1/3 power y instead of x, which by coincidence equal to this one. So after you do this, you can conclude that this is equal to f of y, the marginal distribution of y, and since it is equal to the conditional distribution. So again, this is the original definition or the original way we think of independence. So since the knowledge of x did not affect or did not change the distribution of the values of y, that means that x and y are independent. So in this example, we can conclude that x and y are independent. In this example, he says that we have a manufacturing company that uses two inspecting devices. The first inspector monitor is able to detect 90% of defective items it receives, whereas the second is able to do so in 95% of the cases. Assume that 3 defective items are produced and sent out for inspection. So we have 2 ways of inspection. One of them is successful 90% and the other is successful 95%. And successful here means that it can detect the defective item. And we have a sample of 3 defective items, or 3 items that are known to be defective. Let's define random variable x, which denotes the number of items that are identified as defective by device 1. So device 1 is used to detect or examine the 3 defective devices, and whether it succeeds in detecting the defect or not determines the number of items that are considered defective out of the 3 defective items. So that number is denoted by x, and y denotes the number of items that are identified as defective by device 2. Assume that the devices are independent. So that means we have to assume whether this assumption is true or not. However, it is meaningful to be true in this example, but he says that the 2 devices are independent, which means that the result of the 2 devices are independent, which means that x and y are 2 independent random variables. And he says determine the joint probability of x and y. So we have no information about how x and y are related except that they are independent. So actually, this is how we will start our solution. So since they are independent, since x and y are independent, he said so, that means that f of x and y, the joint distribution, equals f of x times f of y. And of course we use the subscript x here and the subscript y here to know which f refers to which random variable, which BMF refers to which random variable. So the question here is, can we find the marginal distribution of x and the marginal distribution of y or not, in order to find the product of this distribution and eventually we get the joint distribution. Of course, each of the two random variable x and y are very simple distributions because they are exactly binomial distributions, because we have three defective items and we want to test or find the number of items that are successfully detected as defective or not. So actually fx of x is, out of the three, how many will be successfully detected, where the probability of success was 0.9 power x and the probability not to detect is 0.1 or 1 minus 0.9 power 3 minus x, for which values of x. So again, either no item is detected as defective, or 1 or 2 or the three of them. Similarly, fy of y is equal 3cy, but here's the second device, the success rate, its success rate was 95%, so 0.95 power y, 0.05 power 3 minus y, and we have y equal to 0, 1, 2, 3, and we can say easily that the joint distribution, which is the required, is the product of these marginal distributions. In this part, we will be discussing the joint distributions of continuous random variables. As with discrete random variables, jointly distributed continuous random variables are described by the joint probability density function, and we denote the probability of the intersection of such two continuous random variables as f of x and y. As with any probability density function, this should satisfy the main conditions that it is always positive, larger than or equal 0, and that the summation, or in this case the integration of all the joint distributions for all possible values of x and y is equal to 1. Note here that since x and y are continuous random variables, then the accumulation or the summation of the joint probability density function is calculated via double integral 1 over all the range of x and 1 over all the range of y. And if we want to calculate the probability that the two random variables x and y fall within a certain region, where this region is defined by a subset of the range of x and a subset of the range of y, we accumulate the probability density function, the joint, over this area, and again we do this via double integral 1 over the range of x and 1 over the range of y. Similarly, as we did in the discrete random variables, we might be interested in calculating or finding the marginal probability density function of each of the two random variables, and we do it the same way we did before. The only difference is that instead of summation or summing f of the joint distribution over all the values of one of the random variable, we do this via integration. So if we want to find the probability density function of random variable x, that should be independent or irrespective the values of y, so we do it by calculating the integral of the joint distribution function over the other random variable, which is y, and of course here the integration is over all the range of y. Similarly, we can find the marginal distribution of random variable y. Also, the condition of independence is the same as we discussed before for discrete random variables. So two random variables are independent if the joint probability density function is equal to the product of the marginal probability density functions for all the values of x and y which fall in the range of x and range of y. As we said before, this condition is sufficient and necessary. So if we know the condition is satisfied, then the two random variables are independent. And if we know that the two random variables are independent, then we can conclude this condition. Also, if we want to calculate the conditional probability density function of one of the random variables given the other one, for example, here if we want to calculate the conditional PDF of y given a specific value of x, so we do it by calculating the quotient of the joint probability density function by the marginal probability density function of x at the given value of x. Of course, since the conditional PDF is a valid PDF, it should satisfy the conditions that f of y given x, which is of course function of y, should be larger than or equal 0, and it should satisfy also the rule of total probability, which is the integral of f of y given x dy over all the values of y should be equal to 1. Let's try this example together. The example says that we have a random variable x which denotes the time until a computer server connects to your machine, that's in seconds, and y denotes the time until the server authorizes you as a valid user, again in seconds. Generally, it is noted that the formal is less than the other, which means that the random variable x is less than the random variable y. Of course, it makes sense. We cannot be authorized access to a server without first connecting to this server. That's why y is always larger than x. And we are assuming, or we are given, that the joint PDF for x and y is given by this exponential expression. We have a set of requirements, so let's address each one of them individually. The first requirement says that it is needed to verify that the joint PDF is a valid PDF. And again, in order to verify this PDF, we need to calculate the double integral of the joint distribution, and this integral is over all the range of x and y, and in order to validate this PDF, the result should be equal to 1. Of course, we need to calculate this integral accurately, so let's first define the range of x. X is the time needed until connection, so it ranges from 0 to infinity, and then y is the time needed for authorization, and according to the given condition, y ranges from x to infinity. We have to be very careful when we write the limits of the integrals because they make a huge difference in the final result of the integral. So again here, since we have a condition that x is less than y or y is larger than x, then the limits of y are from x to infinity. Substituting for the joint PDF with its expression, which is 6 e power negative x e power negative 2y, we can calculate this integral. Of course, when we calculate this integral, we have to make sure in what order we perform the integrals. Of course, we cannot do an integral over x followed by an integral over y in which one of the limits of y is x. So we need to rearrange the integral, so it should be such that the inner integral is over y and still it is from x to infinity, and the outer integral is over x, where x from 0 to infinity. This integral can be written as follows. It's integral from x equals 0 to infinity. 6 e power negative x is independent of y, so it can be taken outside. and then we have the integral of y from x to infinity for e power negative 2y dy, and then we have dx for the external integral. This is equal to integral of x equals 0 to infinity 6 e power negative x, and the integral for e power negative 2y is 1 over negative 2 e power negative 2y, and we substitute once by infinity and once by x. This, after substitution, results in half e power negative 2x dx. So we have 3 outside, and then we have the integral for x equals 0 to infinity for e power negative 3x dx, which can be easily verified that this integral is equal to 1. So again, to verify the validity of a PDF, we have to calculate the area under the curve, and again, the area under the curve here is a two-dimensional integrals that need to be calculated for x and y, and make sure that this integral is equal to 1. Similarly, we could have been given this PDF with a constant k instead of the 6, and we are asked to find the constant k. So we follow the same procedure to find the value of the integral in terms of k, and since this PDF should be valid, then the integral should be equal to 1, from which we get the value of k. The second part says if a customer is satisfied if the time until a computer server connects to his machine is less than 1 second. So that's the time for connection is less than 1 second, and that until the server authorizes him as a valid user is less than 2 seconds. So that is y is less than 2. What is the probability that the customer requirements are satisfied? So simply it is the probability that x is less than 1 and y is less than 2, and again this can be calculated as a double integral for the joint PDF, which is 6 e power negative x e power negative 2y, and for y it ranges from x, and the maximum value for this sub-region is 2 as per the required satisfactory condition, and x is from 0 to 1. So again, we calculate the integral over y first, followed by the integral over x, and the rest is a straightforward calculation for the integration. The next requirement is to find the marginal distribution and to check if x and y are independent or not. So as we said, the marginal distribution of x is calculated by the integration of the joint PDF, which is again 6 e power negative x e power negative 2y over the range of y. And again, we shouldn't forget that y ranges from x to infinity. So of course this will be a function of x, that will be 6 e power negative x, and since we calculated that the remaining integral in a previous step, and we know it will be half e power negative 2x, so we get 3 e power negative 3x, and we shouldn't forget to specify the range of x, which is x is larger than 0. Similarly, if we want to calculate f of y, we integrate over the values of x, that's from x equals 0 to infinity for 6 e power negative x e power negative 2y dx. So that's 6 e power negative y 2y, which is a constant, and then the integral of e power negative x integral of e power negative x dx, where x equals 0 ranges from 0 up until the upper limit, while it is in general infinity. However, since we are calculating the probability of y, so we have to respect this condition that x is less than y or y is larger than x. So the upper limit of the integral here will be equal to y. So again, this will be 6e power negative 2y times this integral is very easy and straightforward. So we get 1 minus e power negative y, where again specifying the range of y is larger than 0. Of course, since the product of the marginal distributions is not equal to the joint distribution, then these two random variables are not independent. If we want to find the expected time until the server connects to the machine, so this is the expected value of the random variable x, so simply it is integral of x f of x dx. So we have the PDF of x, and we know that it ranges from 0 to infinity. So calculating this integral is very straightforward and gets us the expected time until the server connects to the machine. If we want to find the probability that the time until the server authorizes you exceeds 2 seconds, so again, this is a question in which we should be able to translate the required to probabilistic expression, since he asks about the time needed until the server authorizes the user, so this is y, and it exceeds 2 seconds, so we have to find the probability that y is larger than 2. Again, this is the integral of fy of y, integral of the marginal distribution for y larger than 2, which means that y ranges from 2 to infinity. The last requirement is an example of conditional probability, where we are asked to find the probability that y ranges from 1 to 2, given that x equals 1.5. So this is conditional probability. We want to find a probability for y given x. So if we want to calculate it in general for any value y, this is the joint distribution f of x and y divided by the marginal distribution f of x. Since this one was 6 e power negative x e power negative 2y and f of x was 3 e power negative 3x, so we can calculate this easily. And then in order to find the probability that y ranges from 1 to 2, we have to integrate the resulting expression from 1 to 2. However, we have to note here that given that x is equal 1.5 and given the knowledge that y is larger than x, so we know that y cannot be in the range of 1 to 1.5. You cannot get authorized in time less than 1.5 seconds if you need 1.5 seconds to log on or to get connected. So the limits of the integral in this case will be, instead of from 1 to 2, they will be from 1.5 to 2 because of the condition that x is equal to 1.5. This is another example where we assume that the time until connecting with the server in seconds is exponentially distributed with a mean of half seconds. So we know that we have, let's call this a random variable x, and since it is exponential with mean equal half, recall that the mean of the exponential random variable was equal to 1 over lambda. So our lambda here is equal to 2, the reciprocal of 1, which means that f of x is equal to 2 times e power negative 2x for x larger than 0, and the authorization time is another independent and exponentially distributed random variable with mean equal 1 second. So in this case y is an exponential random variable with lambda equals the reciprocal of 1, which is 1. So again, fy of y is equal to e bar negative y, where y is larger than 0. And we are asked to find the probability that the sum of both connection establishment and authorization does not exceed 1 second. So we want to find the probability that x plus y does not exceed 1 second, which means it is less than or equal 1. In order to get this, we need to have, or we need to find the joint distribution. But since it was said that the two random variables or the two times are independent, then we can say that the joint distribution is the product of these marginal distributions. And the rest is straightforward, because this is an area in which x plus y is equal to 1, so that can be easily translated into a double integral of the joint BDF, which is again the product of these marginal BDFs. So it is e bar negative 2x, e bar negative y. And then if we start with y, so it will be ranging from 1 until the edge of this region, which is 1 minus x, and x itself ranges from 0 again to the edge of this region, which is 1. This is an integral which is similar to the one that we calculated before, and we can calculate it to find the required probability. One more example is about two random variables, x and y, which are uniformly distributed. So we know their distribution to be uniform over the region determined by, for x from 0 to 4 and for y from 0 to x plus 1. And again, we want to find the joint distribution in a certain region, which is x less than 2 and y is larger than 1. In such problems, we might be interested in drawing the region over which the BDF is defined. So we know, or we are given, that x ranges from 0 up to 4, while y is defined in the region from 0 up to x plus 1. So if we draw the line which represents x plus 1, we know that it will be a straight line with a slope equal 1, and the y-intercept here is equal to 1. For x ranges from 0 to 4 and y ranges from 0 to x plus 1, we have this region which determines the range of x and y. And of course, if we want to find the joint distribution f of x and y, we have to make sure that the total probability in the area of validity of the random variables is equal to 1. So this is the double integral of f of x and y dx dy is equal to 1, and this area is the shaded area. Since we know that x and y are jointly uniformly distributed, then f of xy will be constant. So simply, if we calculate this area and equate it by 1, we get the required BDF. Of course, this is an easy to calculate area because it's an area of a trapezoidal, and as you can double check, the joint BDF f of x and y can be calculated as constant k, which is equal to 1 over 12 in this example. So in order to find the probability that x is less than 2 and y is larger than 1, let's determine this area. X is less than 2, so that is up until this point, and y is larger than 1, so y should be larger than 1. So this is the area shaded in green. So it can be easily calculated that this area is 2 times 2 times half. This is the area of the triangle multiplied by the BDF itself, which is 1 over 12. So we get 1 over 6. So when we deal with uniform distributions, it is very easy and very straightforward, because we know that the BDF is constant, and this constant can always be taken outside the integral, and the integral can be easily calculated as the area under the curve once we successfully determine the range of x and y, or the region over which we are calculating the probability. Next, we will be focusing on the calculation of the expectation, variance, and correlation of two random variables that are jointly distributed. It is no surprise that the definition of the expectation and the variance and any general moments of jointly distributed random variable will follow the same approach that we discussed before. So if we have a general function of x and y, phi of x and y, and we want to calculate the expected value of this function, phi of x and y, for discrete random variables, we have to calculate it by double summation of phi of x and y multiplied by the joint distribution, while for the continuous random variables, we do it by double integral for this function multiplied by the joint BDF over the range of x and y. This value, or this function, phi of x and y, can be any function. It can be just a function of x, or function of only y, or function of both of them, x and y. In all cases, we have to calculate the double summation of this function multiplied by the joint BDF, or double integral of this function multiplied by the BDF. And we might have some interesting results here. One of them is that the expected value of two functions added together or subtracted together, or any linear combination of two functions, that will be equal to the same linear combination of the expected value of individual functions. So if you want to calculate the expected value of phi plus psi, that will be expected value of phi plus expected value of psi. And of course, this relation is easily derived or proven from the linearity of the summation or the integration process. The next two relations are very important, and they are very specific for independent random variables. The first of them is that the expected value of xy, this is the product of x and y, as if we are defining phi of x and y as x times y. If the two random variables are independent, then this expected value, or the expected value of this product, is equal to the expected value of x times the expected value of y. Of course, this can be proven knowing that for independent random variables, the joint distribution is equal to the product of the marginal distribution. So only for independent variables we can replace the joint distribution with the product of the marginal distribution. And since phi of x and y is x times y, so if you solve this double integral can be rewritten in a separable form, in which you have integral for x times f of x dx, and another integral over y f of y dy. These two integrals can be easily recognized as the expected value of x times the expected value of y. So again, this relation is valid only if the random variables are independent. So we have to note here that this relation is not a necessary relation for, sorry, it's not a sufficient relation for independence. So if we know that the random variables are independent, then this relation is valid, it follows. However, the reverse is not necessarily true. If we know that this relation is valid, that does not mean that x and y are independent, because it might be a coincidence that the expected value of the product of the random variables is equal to the product of the expectations of the random variables. So again, if we know that they are independent, then the relation follows. However, if the relation is valid, that does not guarantee that the two random variables are independent. Another relation for independent random variables is regarding the variance, and it says that the variance of x plus y is equal to the variance of x plus the variance of y, and you can try to prove it yourself using the fact that independent random variables have a joint distribution which is equal to the product of the marginal distributions. Accordingly, we can calculate a new metric or a new measure which is called the covariance. For each of the random variables, we can calculate its variance. However, when we have joint random variables, we can define a new measure which is called a covariance, and it is a measure of the nature of association between the two random variables. It is a measure of how much the two random variables are related to each other. By definition, the covariance of x and y is the expected value of x minus its mean times y minus its mean. So, as if the covariance is defined as the expected value of phi of x and y, where this phi of x and y is x minus its mu times y minus its mean. This expectation can be easily proven to be equal to expected value of x y minus mean of x times mean of y, and again you need to prove this relation. So it is very straightforward, however you have to prove it yourself. We can use the sign of the covariance to indicate whether the relationship between the two random variables is positive or negative. So if the covariance is positive, then the relation between the two random variables is positive. For example, we can say that if random variable x increases, y increases accordingly. However, if the covariance is negative, that means the relation is negated. So, for example, if random variable x increases, then random variable y will be decreasing. So this is the sign of the covariance. The value of the covariance itself, it gives us a measure of how strong the two random variables are related together. For independent random variables, we know from the previous relation that for independent random variables, the expected value of x and y, x times y, is equal to the product of the means of x and y. So in this case, the covariance is equal to 0. So if the two random variables is equal to 0, then by default the mean is equal to, the expected value of x times y is equal to the product of the means, and the covariance is equal to 0. So we can say that if x and y are independent, the covariance is equal to 0. However, the reverse is not necessarily true. If the covariance is equal to 0, that means that expected value of x times y equal mu of x times mu of y. However, this condition does not necessarily imply that the two random variables are independent. So even if the covariance is 0, x and y are not necessarily independent. The only condition that we can use to prove the independence of the random variables is that the joint distribution is equal to the product of the marginal distributions. Let's solve this example together. It says suppose that x is uniformly distributed. This is the notation of uniform distribution, and the parameters are the minimum and maximum of x. So we are given x ranging from -1 to 1, and f of x is constant, and since the area should be equal to 1, so this constant is equal to half, and y is equal to x squared, and we want to find the covariance of x and y. So in order to calculate the covariance of x and y, this is equal to the expected value of x minus mu x times y minus mu y, or it can be rewritten as expected value of x times y minus expected value of x times expected value of y. So let's calculate each one of these values on its own. The expected value of x times y is equal to the expected value of x, and then since y is defined as x squared, so this is x squared here, which is expected value of x cube. So this is the integral of x cube f of x dx, where x ranges from -1 to 1, and f of x is equal to 0 as we calculated a while ago. So this value can be evaluated. Also, expected value of x is the integral of x f of x dx. So this can be calculated. We know all the parameters, and the expected value of y is actually the expected value of x squared, which again can be calculated by integral of x squared f of x dx. So we get all three values that are needed to calculate this covariance. Another definition that we usually use to determine the relation between two random variables, this definition is the correlation coefficient. And the correlation coefficient is a dimensionless version of the covariance. Note that the covariance is the expected value of x minus its mu times y minus its mu. So it has the units of the random variables multiplied by each other, or if both random variables have the same units, so it has a unit of the random variable squared. If we want to use a quantity that is dimensionless, so we use the correlation coefficient, and we define it as the covariance of x and y divided by the standard deviation of x times the standard deviation of y. Or sometimes we might write it as the covariance of x and y divided by the square root of variance of x times variance of y. Of course, you know that the square root of the variance of x is sigma x, and square root of variance of y is sigma y. If you double check, this quantity is unitless, and consequently the range of the the correlation coefficient, it might have values from -1 up to 1. If we have two linearly dependent, fully dependent random variables x and y, then the correlation coefficient will be either 1 or -1. And if we have completely independent random variables, then the correlation coefficient is equal to 0, and of course it follows because the covariance is equal to 0 in this case. Also, if rho is equal to positive or -1, this is an indicator that the relation between x and y is linear. In this example, we are given a random variable z, which has 0 mean and variance of unity. Note here that we are not given the probability density function fully for the random variable z. We are only given the mean and the variance. And we are required to find the correlation coefficient between two random variables defined as x, which is z minus 1, and y, which is z plus 1. We have two methods to solve this problem. Let's follow the systematic method, in which we need to calculate the correlation coefficient, which is the covariance of x and y divided by square root of variance of x times variance of y. Let's calculate each one of them on its own. The variance of x is equal to the variance of z minus 1, and as we know from before that the variance of a random variable does not change by adding a value to this random variable, because this might change the mean of the random variable, however it does not affect the variability of the random variable. So this is equal to the variance of z, which is 1 in our case. Similarly, variance of y is equal to the variance of z plus 1, which is equal to the variance of z. For the covariance of x and y, recall that it is the expected value of x, y minus the mean of x times the mean of y. Of course, we are given that z has 0 mean, so x will have a mean of equal, its mean will be equal the mean of z minus 1, which is equal to -1, and y will have mean equal to expected value of z plus 1, which is equal to the expected value of z plus 1, which is plus 1. And for the covariance, expected value of x, y is actually equal to the expected value of z minus 1 times z plus 1, so that is z squared minus 1. And again, let's write the expected value of x and y here, which we calculated as -1 times +1. So this is equal to the expected value of z squared minus 1, because the scalar can be taken outside the expectation, in addition to this term, which is equal to +1. So we are left with the expected value of z squared. The expected value of z squared is actually the variance of x, because x has 0 mean, so the variance is equal to the expected value of z squared, which is known to be equal to 1. And of course here the variance is 1 and the variance is equal to 1, so the correlation coefficient will be equal to 1 over square root of 1 times 1, which is equal to 1. We could have concluded this correlation coefficient if we noticed from the beginning that x and y are related, and that, for example, x can be written as y minus 2. So x and y are linearly related. They are two random variables that are linearly related, and the relation is positive, and that means that the correlation coefficient is equal to +1. So we can solve this problem either using the note that we mentioned earlier, that linearly related random variables have correlation coefficient of positive or -1 according to the linearity relation, whether being positive or negative, or we could solve it using the definition of the correlation coefficient as the covariance of x and y divided by square root of variance of x times variance of y. So we have discussed jointly distributed discrete random variables, jointly distributed continuous random variables. We knew how to calculate the marginal distributions, the conditional distributions, and finally how to calculate the expectations and variances. We defined the covariance and the correlation coefficient between two random variables.